You ready, Robert? So my name is Connor Casso, and I am a junior in mechanical engineering. I am the Group 2 reporter for the refrigeration cycle. So this is a picture of the typical refrigeration cycle as it would appear in our homes, which is very similar to the cycle that we have performed in the lab during our experiment. During our experiment, we will be adjusting the flow rate to the evaporator side heat exchanger, and we'll be observing the corresponding temperature changes and pressure changes as a result of that change in flow rate. So these are some pictures of some vapor compression cycles, starting off with the temperature entropy cycle, the pressure volume cycle, and the pressure enthalpy cycle, which is the cycle that we will be referring to during our experiment. So this is the overall refrigeration cycle. The cycle starts off in the compressor where work is input and moves on and is compressed compressed into a high pressure vapor. It's moved on into the condenser where it is condensed down into a high pressure liquid at a high temperature, and is then moved on into the expansion valve where it is reduced down to reduced into a low pressure liquid, and then into the evaporator where it is transformed, or it evaporates into a low pressure vapor, and then this cycle restarts. This is the experimental apparatus, and during our experiment we are looking to find the overall inlet power into the compressor, the overall produced heat and the coefficient of performance, as well as putting our results or interpreting our results in the form of a pH diagram. I labeled the diagram in terms of where we're collecting data throughout the experiment. So starting off with the inlet of the compressor, the outlet of the compressor, the outlet of the condenser, and then the outlet of the thermostatic expansion valve. So the thermostatic expansion valve works to regulate flow of refrigerant through the expansion valve and reducing the pressure so that it can evaporate in the evaporator. So this is our in-lab apparatus. So starting off here, this is the valve that regulates the flow into the evaporator side heat exchanger that we will be adjusting periodically throughout the experiment to adjust the flow rate. The valve if you can see it, it's in the top right of the picture. That's a thermostatic expansion valve. And then the picture on the left is just the receiver that collects all the data from the various instruments throughout the experiment. So one of the main goals was to find the coefficient of performance, which we also needed to find the produced heat and the inlet power. So I started off by finding the mass flow rate of 0.09 kilograms per second with a produced heat of 13.9 kilowatts and inlet power of 1.8 kilowatts. And I found the coefficient of performance by dividing the produced heat by the inlet power, where I found a 7.4 coefficient of performance. The coefficient of performance is important to understand the efficiency of our refrigeration cycle, and it can be influenced by heat loss throughout the experiment that isn't accounted for, as well as like heat gained into the experiment due to like the compressor overheating or something along those lines. Engineers typically use it to optimize and design the refrigeration cycles to run as efficient as possible. So our cycle operates as a real cycle because we are having heat losses throughout the experiment, and so our efficiency isn't maximized, whereas an ideal cycle operates at a maximum efficiency under ideal conditions. So cases 1 through 3, we started off at a flow rate of 6 liters per minute and then moved down to 4.5 liters per minute and then 3 liters per minute. So as we decreased the flow rate, the temperature overall increased. So as the slower the liquid moved through the compressor, the less time there is for heat transfer throughout the liquid. So we ended up with a higher overall temperature at 3 liters per minute. So this is the case 1 where I found an enthalpy of 407, state 2 428, and then state 2 at saturation 418, and then state 3 and 4 where adiabatic throttling takes place. I found the same enthalpy, so 251, and then this is just a graph of the pressure enthalpy chart. So the next 2 cases are pretty much the same. I mean, the temperatures don't change a whole lot, so the data overall doesn't, or the enthalpies don't really change much either. And then I found some uncertainties. Mainly it's like due to leaks or because we didn't let the system go down to steady state long enough, as well as the energy or the power altered as well.